Hey guys, today we're going to look at transformations, specifically going from the equation of a trig function to a graph. So yesterday I introduced to you guys the idea of amplitude, period, phase shift, and vertical shift or vertical displacement when looking at an equation. So we're going to take a second and pause the video here and see if we can complete this information and fill it out. So now that you've had a second to try this on your own, you should have taken the absolute value of your A value here in order to find your amplitude. So you should have got your amplitude as 4. Period is 360 over your K value, which in this case is 1 over 2. So when we flip and multiply, we get 270 for this. Phase shift, our D value is 30. So that means we're doing 30 units right. And I'll fill out vertical shift here. That's going to be up 4 units. And then yesterday we talked about locating our C value or our midline and counting up and down from that the amplitude in order to find the max and min. So if I count up the amplitude from the C value, I should hit my max. And if I count down the amplitude from my C value, I should hit my min. So if I go up 4 units from the C value, which is 4, I should hit 8. And if I go down 4 units from 4, I should actually hit 0. So that should be your max and min here. Okay, now we also took some time yesterday to do a little investigation of what the graphs of sine and cosine look like. Now we had a whole big table of values all the way from 0 to 360 going by 30 degrees. When we do transformations, we kind of focus in on some really essential key points here. So I'm going to go back to that investigation just to show you the key points. So taking a look at our table of values for sine and our graph for sine that we did in our previous lesson, there's a couple key points that we're going to use when we do transformations. Now, if you wanted 2 cycles, you could also use the same kind of similar key points from this cycle on the left, but I'm going to focus on this first cycle from 0 to 360. And the key points are kind of like the maximums, middles, and minimums. So we're going to use the point 0, 0, 91, 180, 0, 270, negative 1, and 360, 0 when we do our transformations. So if you have your investigation on hand, you can star those and make sure that you kind of have those ready. We're going to rewrite them on our lesson today as well. And then when we look at our cosine graph, we want the same thing. So we want our middles, maximums, and minimums. So we're going to have these 5 key points from the first cycle of cosine from 0 to 360. So those will be the points 0, 1, 90, 0, 180, negative 1, 270, 0, and 361. So let's hop back to our lesson here and copy out those points. All right, so I've copied these out on our lesson. And a couple things that I just want to point out here are that the x values of sine and cosine are actually the same. So there's no need to even memorize here. If I know 0, 90, 180, 270, 360, I can plug these directly into my functions for x, and that should give me out the y values. So I don't need to memorize the y coordinates here. And you guys really already have these 0, 90, 180, 270, 360 kind of memorized out. They're the values that are on each of the outsides of our coordinate grid when we did our trig geometry work. So if I just remember those, I go by 90s. That's all I really need in order to generate these set of points. Okay, also always remember we're kind of paring this down to the essential maximums, middles, and minimums, but these are nice, smooth, curved graphs, so I don't want to see any zigzags out there when you guys do transformations. Okay, so we're going to apply our previous transformations knowledge in order to apply transformations to sine and cosine graphs. We call sine and cosine graphs sinusoidal functions. So we're going to start with our key points of sine x, and I know that I'm using sine x because there's a sine x in the function. And we're just going to copy out that x and y from above. And then just as a reminder for you guys, when you set up your new table of values for your transformed function, we want to do reciprocal of k times x plus d, always making sure that we switch the d value that we see in the equation because it's opposite. And then we'll do a times y plus c to calculate our y's. And we looked yesterday at the equations for how we can see transformations of sine and cosine. So I'm just going to hop back to those for a second so you can see. So you'll basically see a, k, d, and c in this format in your sine and cosine functions. We do want to make sure that k is common factored out from the x and d, but we basically should see them kind of like left to right. And if we have a k or a d, it will be found in brackets inside of sine or cosine. So I want you to take a second and consider what you have in this function here, g at x. What do we have out of a, k, d, and c? Okay, so if you answered a as 2 and c as 1, you would be correct. There's the k here is 1 and the d here is 0. So there's no changes to the x's. So I'm simply going to just recopy out the x's here. No horizontal changes. And for the y's, I'm going to do 2 times y plus the c value, which is 1. So I'm going to take each of these y's here and multiply them by 2 and add 1. So what we should get is for each of the zeros, we'll just get 2 times 0 plus 1, which is 1. For 1, we'll get 2 times 1 plus 1, which will give us 3. And for negative 1, we'll get 2 times negative 1 plus 1, which is negative 1. And we are going to graph one cycle of the parent function, and then we'll see how many we can fit of the transform function. I think it'll be one cycle as well. So parent function, we're going to start by graphing each of these points. 0, 0, 91, 180, 0, 270, negative 1, and 360, 0. Okay, make sure, guys, no zigzags like this. We want to make sure that these have a nice smooth curve on them. So make sure that you're graphing these with the curve, like so. That part wasn't great. Okay, do your best with it. So maybe we'll call this f at x equals sine x, or y equals sine x, doesn't matter. Okay, and then for our next one here, we're going to graph our new points, 0, 1, 93, 181, 270, negative 1, that one actually stayed the same, and 361. And we're going to complete that by attaching these in a nice smooth curve again. And these functions do technically continue in both directions. So you are going to add 2 little arrows on the end there. And we'll label the graph. Okay. So there's our transformed function. Now we're going to describe the changes to amplitude, period, and number of cycles between 0 and 360 from our regular graph of sine x to our new graph. So we're just going to draw that down here. So first graph was sine x, and our next graph that we're going to compare is 2 sine x plus 1. Okay, and if you remember from our previous lesson, we talked about how the amplitude of the regular sine function is 1. Its period is 360. Okay, that's the horizontal length of one cycle. And the number of cycles between 0 and 360 is actually equal to the k value. So the k value is actually going to tell us exactly how many cycles fit from 0 to 360. And in this case, our k value of a regular sine function is 1. So in our new function here, amplitude is really the absolute value of the a value, but we can also see visibly here, if we mark off kind of like our midline, you can see that it takes 2 units to get from resting point to maximum and resting point to minimum. So, or the midline, in other words, is what we call it. So amplitude here, just as it shows in the equation, is equal to 2. And then period, we can calculate by doing 360 over k, but really there were no horizontal changes here, so there should be no changes to the period. So the period should still be 360. And if there's no horizontal changes, that means that the number of cycles from 0 to 360 should also remain the same as well. The k value is 1, so 1 cycle fits between 0 and 360, and we can see that in our graph as well. Only 1 cycle is there. All right, let's try another one. We are going to graph h at x, which has a parent function of cosx this time. So I'm going to say, f at x equals cosx, and we'll copy down our key points for cosx here. So there they are from above, and we will identify a, k, d, and c and create our transformation equations here. So basically we're just moving left to right. This is a, k, d, and c. This one's usually pretty easy to set up. You're going to do negative 1.5 times y plus the c value, which is 0.5. Okay, for the x equation here, we want to do reciprocal of k, which is 1/3, plus the d value. So remember, we're always switching the sign that we see in the equation here. Okay, so pause the video, take a couple seconds to fill in your calculations here. So this is what you should have got for your calculations. You may also notice that because our original x's are all 90 units apart or 90 degrees apart, that your transformations should all, as far as x's, be the same number of units apart. So as soon as you start to see the pattern here, 30, 60, 90, I'm noticing that we're adding 30 to get to the next one. I can extend by just continually adding 30. I don't necessarily need to do every single calculation once I see the pattern in here. Also, if I were to do 2 cycles of this, I can simply continue this forward and start repeating my pattern of y values. So I'm going to show you that when we graph here. So I want to graph here 1 cycle of the parent function, and we're going to do 2 cycles of the transformed function. Actually, you know what? We're going to see how many cycles we can fit between 0 and 360 for that one, actually. So that was sine that I was starting to graph. So let's graph cosine, making sure that when we connect these, we do a nice smooth curve. Okay, so there's our parent function. We'll call this f at x equals cosx. And we're going to start by just graphing what we can see in our table of values, and then I'm going to show you guys how we can extend this further. So 30, negative 1, 60, 0.5, 92, 120, 0.5, and 150, negative 1. Now, if you want to, you can kind of like extend your table of values here. You shouldn't really need to once you kind of get the hang of this, but for now, if you wanted to, you could kind of just keep adding 30s in order to extend your graph. So this will be 180, 210, 240, 270, and so on. And basically what we're going to do is just repeat this cycle of y values. So after negative 1 comes 0.5, and then after 0.5 comes 2, and then after that comes 0.5 again, and then we're back to negative 1. So there's another full cycle there. So we're going to see if we can maybe extend this after this next one without having to actually write down all the coordinates. Okay, so you should start to notice kind of like this nice little repeating pattern here. So this is the same as this, and this part kind of coming down here is the same here, and coming down to that minimum is the same. So the idea is we just want to repeat this pattern. So if I go over to the next point here, so if I'm coming over this way, I'm kind of just tracing along the first section of that cycle, or even this section of that cycle. So I know that my next point goes up to 0.5 here. Okay, and then tracing further, we go up to 2 from there. So you're going to go over that same number of units. This one just so happens to be like every unit on the graph, and then up to 2. and we'll connect those. Okay, and then we just want to finish the cycle, so we're going to go down to 0.5, and that's done at 360. But I'm noticing that I can extend this backwards into 0. So if we think about extending this backwards, let's just use the highlighter here so we can see. If I start at the minimum and I want to go backwards, I'm going up to 0.5, and that's going to be 30 degrees over. So 30 degrees over, I should be going up to 0.5. So if you kind of see the pattern, if you're good at kind of picking out patterns like that, you'll kind of visually get an idea of how to extend the cycle. And then you can visually see here as well that we were able to basically create a repeating pattern. So here's one section, here's the next section, and then it repeats again to the next section. And it should kind of always, oh, I just noticed that I graphed this point incorrectly. This point should be down here at 0.5. Sorry about that. There we go. Yeah, so you should kind of notice here that the graph actually starts where it finishes if I have full cycles in there. So this is one section, and then it starts again, and then it starts again, and finishes at this point, kind of like where it started. Okay, so let's take a look at the changes between our original cos graph and our new one. Okay, so our original cos graph has the same properties as the sine graph. So it has an amplitude of 1, a period of 360, and the number of cycles between 0 and 360 is equal to the k value, which is 1. Okay, our new graph, if we look at our a value here, we can actually see that our amplitude has changed. Our amplitude is the absolute value of negative 1.5. So our amplitude is 1.5 units. If I look at the total number of units from minimum to max, negative 1 to 2, and I half that, that should also give me my amplitude visually on the graph. So from negative 1 to positive 2, that's 3 units. And if I half it, I get 1.5. Also, we can see here that one full cycle actually takes, I'm just going to highlight it off for you here, takes from 0 to 120. That is the horizontal length of or displacement of one full cycle there. You can also measure it from like min to min or max to max. So if you measured it from, let's say, 30 to 150, the number of units between that is 120. So that's our period. I know we can also find this by doing 360 over the k value as well. Okay, and the number of cycles between 0 and 360, if we look at this on our graph, we can actually see that there's 3 full cycles that fit between 0 and 360 now that we've filled the whole graph. Or I can simply look at my k value. My k value is 3, and as I said before, this actually tells me the number of cycles between 0 and 360. So now 3 cycles fit between 0 and 360. Okay, and we're just going to try one more today. So I want you guys to actually pause this one and see if you can do this one on your own, and then we'll take it up together. So this is what you should have got for your points. You may start to notice as you're graphing these that these kind of go past the 0 mark into the negatives, which is fine, but we do want to try to fill from 0 to 360. So as you're completing this, it's helpful to know how many units are between each of these, but also it's helpful just to kind of visually look at the space between your points and see if you can extend those. So see if you can get the first initial graphs on here, and pause the video again and see if you can extend our new graph j at x all the way from 0 to 360. So I've now got my first cycle drawn out for my transformed graph, and I have one cycle of my new graph. And I want to show you guys kind of what I do to extend cycles when the points aren't necessarily super nice and I don't want to do a whole bunch of extra calculations. So basically I'm looking like I did last time just to continue this pattern downward, And what I'm really visually looking for is kind of, once I've estimated the space, I'll look for the space between like ticks, is kind of what I call them, and try to duplicate that space over here and graph from there. So I think that that kind of looks visually good to continue this cycle. Now, if you feel like you'll get confused with this, you can definitely just figure out how many units are in between 60 and 37.5 by subtracting them. You should find that you're basically subtracting 22.5 as you go downward this way, and you can also extend your graph toward the positives by adding 22.5. So you can definitely do this as well, or even just have it in your calculator so you have an idea of where to place this approximately. So for instance, if I add 22.5 to 60, I should be placing this around 82.5 here, which I think is pretty accurate around there. So lots of different ways that we can do this, but I'm kind of like a visual person, so I just kind of look at the space between the points and extend that way. Okay, so the next one that we're going to do is we're going to go up, and this one is exactly halfway between 0 and 30. It is 15.2. So the next point that I do, I want to go up to 2, and I want to put it exactly halfway between the next two ticks. So that's this one here. I'm going to go up from there. Okay, so that's the idea. We're going to go up to the next one. Now the next one should be slightly past. It's about 7.5 units past 30 here. So my next one should be the same. It should be about 7.5 units past 120. So when we go up here, I'm going to go like right here-ish. Okay, it should visually, the space should kind of match between here and here. So that's up to the max now. Okay, and then to complete the cycle, we're going to go back down to 2, and this should be exactly on the next tick over. So when I go down here, I should go exactly on that 150 mark, like so. Okay, and then we're going to just repeat the process again. So now we're basically back at this initial point here, and we're going to continue kind of looking at that spacing again, or continue adding on our calculator so that we can get the next section. So kind of like going down like this, making sure that my point is like just before 180 mark. Okay, to complete that section, and then up to 2, making sure my point's exactly halfway between these two ticks. This wasn't great for curving this around. Here we go. Okay, next point over, you're going to make sure you go past the next little tick by about 7.5 units. So right there. And then the next one to finish off this cycle, going down to the next complete, the actual tick there. Okay, and then I'm just going to continue that again. So I'm going to go a little bit quicker for this one. And I'm going to finish this off at, actually I won't finish exactly at 360, but this next one will go right before 360. So that just about, I guess like 360 would kind of end like right there, kind of like where this one starts at 0. Okay, I actually can see from my K value, however, that 4 complete units should actually fit between 0 and 360. It just might not, based on the points that we have, might not start perfectly at 0 and go to 360. But you can kind of see here that 1, 2, 3, and 4 cycles fit. Okay, so when you go to describe your changes here, if you haven't done this yet already, our base function is sinx that has an amplitude of 1, period of 360, and 1 cycle fits between 0 and 360. Okay, our new function j at x has a new amplitude, and that amplitude comes from this, actually it doesn't have a new amplitude, sorry, I'm thinking of the last one. Amplitude, the A value here is actually still 1. There's no vertical stretch or compression, so the amplitude of this should still be 1. And we can actually see that on the graph here. That displacement there is 1 unit. Period here has changed, however. Like we said, the K value was -4, and to calculate period, we do 360 over the absolute value of 4. So just the positive version of that. So your period should actually be 90. And number of cycles between 0 and 360, if we take the absolute value of K, that should tell us the number of cycles. So that should actually be 4 units between, or 4 cycles between 0 and 360.